Okay, so as you know already, object-oriented technology allows us to build modular applications by breaking up the application into multiple modules called classes that allow you to reuse code using a technique called inheritance, right? Where you can declare some base implementation, some base behaviors, base attributes at higher level of abstraction classes, and then you can create more specialized versions of those by inheriting from higher levels, right, and deriving from them all their behaviors, all their properties and whatnot, right? And you can have very long chains of inheritance where incrementally more specialized versions of these classes add additional behavior, more specific behavior, more specific attributes. Yes? All right? So there is no equivalent of this concept in relational databases. There's no such thing as classes and inheritance and polymorphism, any of that. Right? That came much later after relational databases was invented and became so pervasive throughout the industry. But nevertheless, we need to be able to model it. We need to be able to represent that same idea somehow in a relational database because we have it so pervasive in our programming languages everywhere, right? So how do we map these two worlds? So there's several strategies. There's 3 strategies in particular. Each one with its pros and cons, and why would you use one or versus another? The 3 strategies are roughly referred to as the joined strategy, also known as normalized, right? The single table strategy, also named also as a denormalized strategy, and then there's the other one, the table per class, a hybrid, okay, a hybrid of the two, right? So these two have pros and cons. This one tries to reconcile the pros and the cons of both and have the best of both worlds, okay. None of them is a perfect solution, right? None of them is a perfect solution to what actually inheritance is implemented in a object-oriented programming language. But nevertheless, it's 3 strategies that work well. So here's a simple example where you have a base class question that captures some of the common things about all questions. Right? You might have a title for the question, how many points that question is worth, some description, and maybe the instructions on how to fulfill that question, how to answer that question. Make sense? And then you have 3 special cases of questions, each one with its own attributes. Right? For instance, a true/false questions. Not only does the true/false question also have a title and points and description and instructions, but additionally, it has attributes such as whether the true/false, the answer is true or false. Yes? So it adds a new property to a special property of the more general case of a question. And then we have fill in the blanks. Fill in the blanks might be you have multiple blanks that you need to fill out, and you need to know which one are the right answers, right? What are the right answers, so they can be compared and evaluate whether you answer it right or not. Yes? So you might have multiple variables that have names and values and whatnot. So it's maybe it's an array of strings. It's irrelevant, the actual implementation. Right? What's important here, what I'm trying to point out, is that they have specific attributes that are specific to that more specific class. Yes, a derived class. Make sense? All right. If you have an inheritance where you don't have any special attributes, then the inheritance is irrelevant. It makes no sense to do an inheritance, but then don't provide anything that is specific to that class. Might as well just state in the more general case. Make sense? All right. All right, so let's take a look at how is that we would implement fill in the blanks, true, false, and the base class. How would you do that in relational databases, right? First, let's look at the joined strategy, right, which is also referred to as the normalized strategy, right? It's typically the more intuitive way to implement it, but it's also the less efficient, right? It's the one that is most expensive to implement, right? So typically we stay away from this implementation, although it's the most intuitive, right? It's the one that one immediately thinks of. For instance, one of the intuitions, one of the things that we would look at intuitively is that, well, we got 3 classes or 4 classes here, right? There should be 4 tables, right? And somehow they should be related somehow. I don't know, but intuitively that's our first approach. Every class has a table, right? And so that's where the joined starts. The join starts with that intuition. We're going to have each class is going to be represented by its specific table, right? So here the table is called joined because that's the strategy we're using, and then base because this is going to be the base class, and then finally this is the question, right? This is the base question class, right? The name doesn't matter. The name doesn't matter. I named it like that so that it keeps me, it reminds me the strategy, the class, right? Whether it's a base or derived, and the actual class that was used to build it. Notice that it captures all the attributes of the generic question. We have the instructions, the title, the points, and the description. They're all there. Everybody good? So that's very intuitive. Plus, we added a primary key, right, just to guarantee the uniqueness of the record that we're storing in there. Everybody good? This is intuitive. This makes sense. What about the other ones, the true/false question? Well, again, it has its own table. That makes sense. Also, it has its own property. Is true. There it is, implemented as a bit, right? Not null. It has its own primary key. That is also intuitive. It makes sense, all right? And the only other thing that we are going to add here is that we want to make sure that this record has no meaning without the other record, right? If you go back to the class diagram and you look at true/false, an instance of true/false, right, can never exist on its own, right? It can only exist with the inherited attributes of the base question. Yes? It has to have, it's meant to be one and the same, right? It needs to have, and we conceptually treat it that way, right? That we understand that this box, because it has this empty arrow here, it also has not only its own attributes, but all the attributes that are inherited from its parent. Yes? But there's no way to enforce that in SQL. There's no such thing. So we need to find a way to enforce that. That this record can only exist, right, alongside with the other record that is in the other table. Right? That half of the attributes are going to live in this record, in this table, and the other half of the attributes are going to live in this other table. Yes? But they're meant to be one and the same. So we enforce that by making sure that the primary key of this record is also a foreign key to the base class, right? To the base table, right? That if the base class ID is 1, 2, 3, my primary key is also 1, 2, 3. Right? And that whenever you want this record, right, the intention would be that you would join it with the other record, and then you get the entire true/false question. You would join the two, and you would get all the fields. Make sense? It's meant to be treated as a join between the two. But there's no way for us to enforce it. Obviously, our algorithms would need to, do the join and retrieve from both tables. But here we are using referential integrity to make sure that there's a one-to-one relationship between the two. Right? If I remove one, I remove the other two. Right? They're part of the same thing. Same thing with fill in the blanks. Right? We have the variables being the special variable the special field that for this specialized table, right, that represents the specialized class that again has a primary key that then refers to the foreign key of the parent class. Yes, right. So this is the joined strategy. It's useful. Certainly you can use it. Here's some examples on retrieving some objects of the particular type. This is a base instance that has particular points, IDs, and a particular title, description, and instructions. And notice that it has an ID 1. This should also be 1. The whole point would be that this is also 1. There we go. And you have the fill-in and the true inheriting from the parent, okay, with its own special field for that particular class. And this is what it might look like in a SQL when you query it, where you have ID 1, description 1, 2, 3, 1, 2, 3, and whatnot, and then references for each one of these, where the true/false is referencing ID 3, and the fill in the blanks is referencing ID 2, which is these two over here, right? This is the true/false and the fill in the blank, storing half of the attributes in one table, and the other half of the attributes stored in each one of these two tables. Make sense? And then you would join them to reconstruct the records. Okay? Right? This is an alternative, and this is what we ask you to do for the person, developer, and user, that you use this strategy. Okay? Now the problem with this strategy and why we typically don't use this strategy is that in object-oriented technology, it's very common that your inheritance chains are fairly deep. Right? You have one very abstract class, inherited by several derived classes, and the chain would be 2, 3, 4, 5, 6 classes deep. Okay? Now, when you in an object-oriented technology, that's no problem. It's very common to have these very deep inheritance chains. In a relational database, actually, it makes it very inconvenient, right? Because that means that if you're retrieving classes or instances, in the shallow part of the chain, you're only joining 1 or 2 or 3 tables. But if you're talking about retrieving data from a class that is way deep in the inheritance tree, you're joining all the tables, right? All the way through the entire chain. You might be joining 3, 4, 5, 6, 7 tables, to be able to reconstruct a particular instance. It would be very expensive to actually implement something like this. Make sense? Right? It would be prohibitively expensive. So instead, the more common way that inheritance is implemented is using the single table implementation, which is also referred to as the denormalized strategy. Right? And we're asking you to use the denormalized strategy for implementing the widgets. Right? For the widgets, instead of having multiple tables, instead we have one single table, a denormalized table. What we do is that for all the classes, all the other classes, fill in the blanks, true, false, all those fields, like is true and all the variables, instead of having dedicated tables for each one of those classes, we're going to collapse all those fields up to the parent. Okay, we're going to collapse it to the parent, even if you have a inheritance chain that is 3, 4, 5, 6, 7 classes deep. They all get collapsed all to the top of the parent. Okay, so the parent, it's not the children inheriting the property. It is the parent who's inheriting all the attributes from the children up to the top. Make sense? Right. So here we have the parent who has all of a sudden inherited the fields from all the children. See that? Now we need to be able to distinguish if we're inserting one type of question, whether we're creating a true/false question or we're creating a fill-in-the-blank question. If it's a true/false question, probably won't have a value for variables, so that's going to stay null, right? And if we insert a fill in the blank, we're going to have values for the variables, but the is true probably is going to be null. Make sense? So in a denormalized strategy, it'll be very common that you have lots and lots of nulls. Right? You'll have values for the side of the table that is the common to all records, right, to all classes. But for the other ones, you'll have values for only a subset, a very small subset of all the fields will have actual values for that particular type, right? But all the other ones are going to be null. Make sense? Right? We also need to be able to distinguish, to remember what was the intention, right? You inserted a fill in the blanks, or you inserted a true false. We need to make a note. We need to make a note. What is it that you inserted in here? Did you insert a true false, or did you insert a fill in the blanks, right? So in the single table strategy, we also add an additional field, right? A meta field, right? To keep track of what was the intended instance type, right? Okay, makes sense, right? So this is a denormalized or the single table strategy, and we're asking you to use this strategy for the widgets, right? You have the YouTube widget, the image widget, you have all these widgets. All those attributes are going to live on the single widget table. Make sense? All right. All right. Yeah. So this is the fastest, right? This is the fastest that performs the best, but it's denormalized. A lot of people don't like it because it's denormalized. The whole point of when we're creating a table is to remove redundancy. Also, we would typically not use this manually, right? We wouldn't interact with this manually. Instead, we would use some kind of API, an API that would know about this, all this magic of how we're mapping inherited chains into these type of tables, and the API would handle the tables for us. We would never actually do it manually, like we're asking you to do it in the assignment. Later on, we will come back to this using JPA and ORMs, and the ORMs will handle these tables for us. Right? We will never actually go in and do it ourselves manually. But nevertheless, it's an educational opportunity to do it manually, at least once. So here's an example on retrieving the different types of questions. Here's our base question, the fill in the blanks, the true false, with their different IDs. Notice that for the fill in the blanks, I don't have either value of variables or is true. For the fill in the blanks, I have values for variables, but not for the is true. And for the true and false, I have values for the true, but not for the variables. Make sense? And I have an D type tells me what the original instance, what it was. All right. So finally, we have a hybrid. Right. So folks oftentimes don't like working with denormalized. They would have preferred to stay in the more intuitive world of having the one table per the normalized solution, right? But it has the problem of being expensive, right? So this one, the per class strategy is a combination of the two. We will have one table per class, but we don't want to run into the issue of the expense of having to join the tables. So what could we do? How would we solve this? Well, the way we solve this is that we have a table for the base class, just like we did for the normalized solution, right? We have this, but then all the children, because I want to avoid having to join, what we're going to do is that we're going to literally do how the objects are interpreted by the object-oriented infrastructure, is that they're going to inherit the actual fields from the base class, right? So instead of inserting only in the parent and having to join the two to be able to reconstruct, we're going to duplicate the data, right? We're going to insert in the parent, and we're going to insert down in the child. So the child is already going to have the data, right, from the parent already there. So there's no need to join it, right? It's already in there, right? So not only do we have the is true, but we get all the other fields. So you get literally the literal interpretation of inheriting all the fields onto the children. And same thing for the fill in the blanks, right? All the fields from our parents come down to us. Notice there's no need to do the D type, right? It's redundant because you already know the name of the table, right? That table tells you what you are, right? So this is the best of both worlds. Okay. All right, I'm not asking you to do this third strategy, although it's as interesting as it sounds. Let's focus on those other two. All right.